Okay, Chem 101 guys. People in lab today said they want video keys. And old Abe Wade has been saying he wanted a video key. So Abe, this is just for you, all right? This is really only for you, and everybody else gets it, just by the grace of your existence or something. So, first one, okay, we need to find the structural formula. What is the structural formula? The structural formula is the one where you show literally every single thing, every single H. You draw the bond to that H, and we show it. Okay. So first thing, we need to go through and make sure we know where all our H's are, right? What I would do is redraw this and just fill in all the carbons first. So remember, any of these corners, that means there's a carbon there. So I'm just redrawing this ring and showing all the carbons right now. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so that's good. Then I need this side. So there's an N to an H to a C to a double bonded C, and then that's single bonded back to this same one. So 1, 2, 3, 4, 5 in that ring. 1, 2, 3, 4, 5. Okay. Now I need to go and fill my hydrogens. Remember, the way you know where to put the hydrogens is that all carbons have how many bonds? That's right, it's 4 total bonds. So any carbon that doesn't have 4, like this one has 1, 2, 3, there must be an H here. 1, 2, 3 to this carbon must be an H. 1, 2, 3, 4, this one doesn't need an H, right? It already has 4 bonds. 1, 2, 3, you get an H. 1, 2, 3, 1, 2, 3, 1, 2, 3. You guys ever seen that Always Sunny in Philadelphia? Charlie's mom always does 1, 2, 3 on the light switch. Okay, that's just what it made me think of. So this would be our structural formula. Okay, everybody has 4, all the carbons have 4 bonds, and we love when that happens. Okay, so let's finish doing structural formulas while we're thinking about it, and then we'll come back and do the functional groups at the end, because we know for sure functional groups will be on this exam. I mean, if we don't know that by now, we just haven't been in lecture for a while. Alright, so again, 1, 2, 3, 4, 5 carbons in this little pentagon. So let me just draw those all in. They're all single bonded to each other. And then these two on this end have chlorines attached. Now I need to figure out how many hydrogens am I missing. Okay, so this carbon only has 2 bonds, so he must have 2 H's. Same thing here. Same thing here, right? It only had 2 bonds first, so there must be 2 H's that weren't shown. And then here, 1, 2, 3, that one must have an H. 1, 2, 3, this one must have an H as well. Okay, so here's my structural formula of this one. If I wanted to do a condensed formula, right, if I was thinking about doing a condensed formula, then I would just call this a CH2, right? I could just draw like a bond to it like this. Okay, that's the condensed formula, is where we just don't show the bonds to the hydrogens, we just say how many hydrogens are on each carbon. Okay, this one, so again, easiest thing to do here, start with the skeleton and draw in all the carbons. So carbon, so 1, 2, 3 carbons, 4 carbons, right? 1, 2, 3, 4 carbons total. Then this one on the end has an NH2, and it has a double bond O. And then 1, 2, 3, okay, 1, 2, 3, between carbons 2 and 3, there's a triple bond. Now I need to fill in my hydrogens. So this guy only has 1 bond, so he must have 3 hydrogens. This carbon has 1, 2, 3, 4, so he's fine. This one has 1, 2, 3, 4, so he doesn't need anything. This one has 1, 2, 3, 4, so he's good too. Okay, so that's my thing. Okay, now we want the skeletal structure, so we kind of just go backwards now, right? I just need to draw in all my carbons first, and then the other stuff. So 1, 2 carbons, right? That's just a line segment. 1, 2 carbons here. Let me draw this a different way so that it matches up with the way this is drawn on here. So these 2 carbons I'm going to represent like this. Okay, so this end of the line is a carbon, this end of the line is a carbon. This one's attached to an oxygen. And remember, in the skeleton structure or skeletal structure, you don't show H's on carbons, you show them on anything else. So I need to show this OH still. Okay, same thing here. So there's my 2 carbons. One on the right has an OH attached and a double bond O. This one on the left has this NH2 group attached. And you could just write that as NH2. I'm going to write it as H2N, just to show that that N is attached to it. Either one would be fine with me. Okay, again, 1, 2, 3. So 1, 2, there's my 3 carbons, then an oxygen, and then another carbon. And these H's are all implied, these H's are implied, this double bond O needs to be drawn. And then this O, and then this H's. Okay. Alright, last one. I have a benzene ring, so just a 6-membered ring with 3 double bonds in it. Well, I suppose I should draw this the way it's actually on here, even though it's the same thing. Because my double bonds on the way I have this structure drawn are like this. Really, these two are the same thing, the way I drew this. But that's not something we care about in this class. Okay, so I have my 6-membered ring, then this carbon attached to it, and then I have a double bond O. You can either draw in this H or not. If you were to draw it like this, that's fine. I just don't like that personally, so I always draw in the aldehyde proton at the end. It's kind of a convention that goes either way. So either one of these is fine. Okay, because we said we don't show H's attached to hydrogen, so if you want to not do that, then I accept you for that. This front and back, okay. Name and label all the functional groups. Okay, let's do this in black. Name and label all the functional groups. So this, well, I'm going to do it in red. I'm going to do it over here. So this is a benzene ring. Right? We don't call something an alkene and a benzene, and I'm not even going to refresh your memory on what these functional groups are, because you really just have to make note cards or flashcards and look at your notes. Or if you didn't take notes or you missed that day, you can find a table of functional groups online really easily, and you know from, there's extra handouts outside my office. You can go grab one so you know which functional groups you're responsible for. So this is an alkene, right? C-double-bond-C is an alkene, and then this N, anytime we see an N, we know that's one. It is for sure a functional group. It's either an amine or an amide with a D, which is an amide, if we want to call it that. Then we can overlook that. Okay, so there's our amine over on that side. Okay, this one, it doesn't have anything. So we have chlorines, but other than that, all we have are carbons and hydrogens with no double or triple bonds. We don't know any functional groups with chlorines, so we would just call this then, or we could even call this whole molecule an alkane, would be our functional group. Remember, alkane is the one, you only call it an alkane if there's no other interesting functional groups. Okay, C-triple-bond-C, Abe, what do we call that? Since I know you're going to watch this video, if I find out, Abe, that you didn't watch this, I'm going to be upset. Yeah, we call that an alkyne. Okay, I wrote it down while I was doing my little bit there. And then this one, we said anytime we see a nitrogen, we know it's something. This one is different from this nitrogen because, right, here's the two major differences. If you just see a regular old nitrogen that's not on a C-double-bond-O, then that's an amine. If it is on a C-double-bond-O, that's an amide or an amide, if you want to call it amide. I'll allow it. Although an amide is something else. This is called an amide. It's called an amide, so let's call it an amide. All right, next ones. What do we have here? Abe. Abraham. What kind of functional group is that? Just this little OH here. That's an alcohol. If it's an OH that's attached to a C-double-bond-O over here, that's different. So you've got to be on the lookout. C-double-bond-Os should kind of perk your eyes up a little bit. Look at what's attached to them to figure out what group that is. C-double-bond-O, OH, that is a carboxylic acid. And then over here, I have an NH2. It's not attached to the C-double-bond-O, right? There's a carbon in between them. So this is still just an amine. It's not an amide. Okay, it's not on the C-double-bond-O carbon. Right, it's one separated off from it. So that's just an amine. Let me better focus here. Where's my focusing thing? For some reason this usually works. Sometimes that helps it focus, I don't know why. Okay, next one, I have a C-double-bond-O, so that really makes me think there's some kind of functional group. And then I have an O, but it's attached to a carbon, so that's different than a carboxylic acid, right? If this is an H attached to the O, we call it carboxylic acid. If it's an R group or a carbon, we call it an ester. And then over here, again, we have benzene. We should be able to pick benzene out with our eyes closed. Okay, you got to be able to pick out the easy meat with your eyes closed, as one might say. And and this is an aldehyde. You guys know what I'm talking about? You guys get that? Anybody get that Pink Floyd reference? I hope so. Okay, aldehyde is when you have a C double bond O and an H attached to it directly. That's an aldehyde. Okay, what's on the back of this? Circle functional groups and give their names. So this is kind of the same deal then. Here's a nitrogen, so that's something. It's not on a C double bond O, so that's an amine. Here's a benzene. We know benzene so well at this point that I'm not going to talk about it. And then what about this? Anytime I have an oxygen, that must be something as well. Kind of like I said, anytime we see an N, that must be something. I have an O attached to a carbon on this side and a carbon on this side, and no C double bond O's in sight. That is an ether. Okay. What do we have on this one? So here's an O. When I have an OH attached to a carbon, that's an alcohol. We already said that. I have a double bond here. That's an alkene. All right, it's not part of a benzene, so it's an alkene. And then I have a C double bond O, but it has a carbon on each side. What do we call it when we have a C double bond O and a carbon, or two R groups on either side of it? That is a ketone. Okay, so it says draw an ether functional group surrounded by two carbon chains. Well, I know this. Don't laugh. Okay, don't laugh. We don't read it out like a word, but I know that this is what an ether looks like. Don't laugh, Abe, okay? COC. And it says surrounded by two carbon chains. So there's a carbon over here, a carbon over here. But this can't be the whole answer, right? Because my carbons they don't have 4 bonds, right? Carbons always have to have 4 bonds. So this must have 3 H's. This must have 2 more H's. This must have 2 more H's. This must have 3. And if you're not sure why I did that, you can go back the video up and just count how many bonds does each carbon have and how many H's do I need to add to get them to have 4. Okay, so there's your structural formula. If I want to do the skeletal structure, okay, just to go to the other extreme, I just say 1, 2 carbons, so there's 2 carbons, then attached to an oxygen, then attached to 1 carbon, 2 carbons. So there's my skeleton. Condensed structure, remember, I'm just going to rewrite, instead of showing all these H's, I'm just going to say, well, this is a CH3, and I know that hydrogens only make 1 bond, so it must be the carbon that's attached to this other CH2, which is then attached to this O, CH2, CH3. Right? I'm just saying CH3, C with 2 H's, attached to either thing on either side, and my O, CH2, CH3. Okay, cis, trans, and neither. Let's do this one first. Okay, when we're looking at cis versus trans, we're looking at which side. We're looking at H's that are on 2 different carbons, okay, of an alkene. So it's always a double bond. We always have to look at H's on either side of the alkene. Okay, or on either carbon, I mean. So I'm comparing this H with this H, and I'm asking, are they on the same side of this double bond, this plane that I could define by the double bond, or I guess line is more accurate, this line that I could define by double bond, are they on the same side of this line, or are they on opposite sides? So these H's are on opposite sides, and when they're opposite, or when they, the side changes, then we call that trans. When the side they're on the same side, okay, it stays the same, then we call this cis. Okay, cis and trans. This one, if we have 2 H's on one carbon and only 1 H on another carbon, then you can't really say it's cis or trans, because it's like, well, these 2 are cis, but these 2 are trans, right? This H is on the same side as this one. This H is on the opposite side of that double bond as this one is. So this is not cis or trans. This is neither. Okay, identify which of the following are chiral, put a star in chiral centers. We can do that, I think. So kind of like I did up here, the thing that makes this easier is if you go through and actually show the missing H's. Okay, sometimes that'll make things a little bit easier. So there's H here, there's H here, there's 2 H's here, there's 2 H's here, 2 H's here, right? So anytime I have a carbon that only has 2 bonds shown to it, that means the other 2 bonds are H's. That can't be chiral, right? So it's like this says. Find a carbon with 3 bonds, fill in a hydrogen, and then see if all 4 of those things attached to that carbon are different. So all these carbons only had 2 bonds. This has a double bond. Double bond can't ever be chiral. This one has 1, 2, 3 different bonds and an H that's not shown. And on this carbon is just a CH3, so that's different than this CH2, which is different than this one, which is part of a double bond. Okay, so it's attached to 3 carbons, but they're all unique carbons. Okay, the difference is if I had something like just like this, okay, now this middle carbon is attached to a CH3, and another CH3. Okay, or even if I made this one different, let's say I make this one a double bond, I'm still attached to 2 CH3 groups. So those are identical groups attached to this carbon I'm looking at. Here, okay, these are 3 unique carbons. So this is chiral, and my chiral center is right here. It's that carbon I was just talking about. Okay, so hopefully this maybe is starting to make a little bit more sense. Now let's look at this one. Okay, so this one can't be chiral. It only has 2 bonds. This one has 3 bonds. This one has 3 bonds. Okay, that one only has 1 bond. So if I look at this one, I would say I have an H, right? I have an H on this one as well. I have the rest of the chain, that's one group, and then I have, this is a CH3. Oh, this is also a CH3, right? This and this are CH3s. And this are both CH3s as well. So neither of these carbons with 3 bonds are chiral. So overall the molecule is not chiral. Okay, same thing. So here's a 3-bond carbon. Let's draw on an H and check her out. So I have a CH3 group, a CH2 group, and then I have this this one only has an H, right? This is a CH right here that's connected to then other carbons, whereas this one on this side is a CH2. So this one's connected to 3 unique types of carbons, a CH3, a CH2, and a CH. Okay, and the smallest change in the structure of these 2 carbons, if they're not completely identical, then we would say that they're unique for the purposes of chirality. Okay, so there's a chiral center, and then this one is one as well. Right, because I have 1, 2, 3 different groups attached, and they're all different. This one's a CH2 that's next to a C double bond O, whereas this is a CH2 that goes on to a longer carbon chain. So if you have to look at what's attached, not just one atom away from where you think a chiral center might be, but all the way down. If there's any subtle difference, then they're not identical groups. Okay, everything has to be the same about them for them to be considered identical. Anything different at all, then they're unique. So this is chiral as well, and this one has 2 chiral centers. All right, Abe, 1 down. I'm going to make the other one now. Here we go.